Welcome to the deep dive. Today we're going into the real theoretical bedrock of modern physics.
We are.
We're looking at the monumental work that basically secured the Standard Model, and our core source here is the 1999 Nobel Lecture from Martinus J.G. Veltman.
Right, and what he and Gerard Hooft proved was, well, it was absolutely essential.
And that essential thing was renormalizability.
Exactly, renormalizability. It's kind of like the mathematical cleanup crew for physics theories.
A cleanup crew, because otherwise the calculations just get messy.
Messy is an understatement.
Right.
Without it, the Standard Model, the theory that describes basically all known particles and forces, it would have been completely useless.
Useless because of the infinities. That's the classic problem, right?
That's the one. You try to calculate how particles interact, and the answers just mathematically shoot off to infinity.
So your theory can't actually predict anything.
Precisely. If your theory generates infinite answers, it's fundamentally broken. Now, there were hints, from earlier work like the Adler-Weisberger relation, that there was an internal consistency.
But the math itself still broke down.
It did. The main problem was with the charged vector bosons, the particles that carry the weak force.
So what was the critical flaw Veltman identified? Where did he zero in?
It was in the vector boson propagators.
The mathematical terms that describe how the particles move and interact.
Exactly, and their structure was just wrong. It generated what Veltman himself called divergency conditions.
And that sounds bad.
Oh, it was a disaster. So bad that it made stable particles look unstable in the equations. I mean, that's a huge sign that your entire framework is broken.
And trying to fix that, I imagine the sheer algebra would be a nightmare.
A complete nightmare. Veltman used the term monstrous expressions. We're talking about thousands and thousands of terms just to check if your fix is working.
So it's basically impossible to do by hand.
Pretty much. And that's actually why Veltman developed his own computer program. It was called Schoonship.
Which is Dutch for clean ship, right? To clean up the algebraic mess.
Exactly. He built it in just 3 months, purely to handle this algebraic avalanche. The tool itself was a critical part of the theoretical progress.
But even with the tool, there was still this huge conceptual problem hanging over everything.
A massive one. You had this simple massless theory that was mathematically kind of clean to renormalize.
But the real world has mass. The W and Z particles are heavy.
Right. So how do you give them mass without breaking all the delicate mathematical machinery you just built?
And that, of course, is where the Higgs connection comes in.
That is the pivot point. The Higgs mechanism provided a way to give the vector bosons mass, but crucially, the Higgs interactions also generated the exact mathematical terms needed to cancel out all those unwanted divergences.
It all just clicked into place.
It was the key.
Yeah.
It finally made the massive realistic theory renormalizable.
So let's bring this home for everyone listening. What's the real so what moment here?
The triumph is that once the theory was mathematically sound, you could use it to make real, concrete predictions. You could use these tiny, subtle effects called radiative corrections to calculate things about particles that hadn't even been discovered yet.
Like the top quark.
Exactly like the top quark. Using these now tame calculations, Veltman and his collaborators were able to put a constraint on the mass of the top quark years before it was found.
Yeah, their prediction was incredibly close, wasn't it?
It was. They predicted it, and when it was finally discovered, its mass was right around 175 JV. It was proof that this wasn't just some elegant theory on paper, it was factually predictive.
It's the ultimate validation, really, transforming this very complex, abstract idea, electroweak unification, into a hard, testable number.
It secured the foundations of particle physics. But, if we're talking about the biggest picture, Veltman's lecture ends with a truly provocative thought.
What's the final idea he leaves us with?
He suggests we should consider that the Higgs field itself, the thing responsible for spontaneous symmetry breaking, might be intrinsically linked to the value of the cosmological constant.
Wow. Okay, so the field that gives mass to the smallest particles we know
could be connected to the energy density that's driving the accelerating expansion of the entire universe.
That is a profound connection. A mystery linking particle physics to the destiny of the cosmos. A perfect place to leave it.